Welcome to day 4 of Programming in Python. I want to give you an update about Prismia before we get into the content. And this is a pretty big one, I think. So the way this new feature works is that when I ask open response questions, I'm able to prescript possible answers that I think you might have, sort of general intents that you might express in response to that question, and then prescript my replies as well to those responses. So when your answers come in, there's some work that's being done both by me and by a natural language model that puts your intents in the appropriate place, and I'm able to send my prescripted response. So that way you're getting more personalized responses that are more thorough. So here's what it looks like from my end. I ask a question and your answers come in, and they're going to be classified here, and then I can send my prescripted replies. And I can also make new ones. That's what this additional column over here is for. So I'm hoping this is going to be really great for you for getting more consistent, more personal feedback, but we'll see how it goes. It might be difficult to anticipate the kinds of things that people are going to say, and well, we'll see. I mentioned this even though it's not a student-facing change, so there's no change in your browser. But I mention this because your motivation to engage with the questions is inevitably shaped by the expectation that you have to receive meaningful feedback or not. So in reality, in order to change this long term, I have to actually deliver meaningful feedback, but it can be hard to sort of bootstrap your way there when folks are sort of feeling like the return on investment for engaging is not super high. So I'll try to set your expectations a little bit higher initially and see if I can deliver as a way of ramping that up a little bit faster. So last time, if you remember, we were talking about a spell correct application, and we're going to continue working on that today, and we're going to finish it. But before we do that, I want to just practice a few of the ideas that have come up over the last few days, just to reinforce those ideas a little bit and also see how it's going with retention of what we learn in class. Here's the first question. So there's no coding here. I just want you to, answer with a sentence. So when I first started programming, I used the following design pattern a lot. I would define an array containing some values, then another array of the same length containing some associated values, and then I would look up the appropriate index and use that to return the associated data. So I can say, for example, that Frozen came out in 2013 using this function. I should not have been doing that. This was very bad practice. What should I have been doing instead, and why? Great. So a few people still typing, but I'll start sharing answers and we can move on. So here's a great answer from Hardy. Here's one from Etienne. You can correct my pronunciation. Would you like to talk about this one? Yeah, that's exactly right. So this is a paradigmatic use case for a dictionary. So we should really use a dictionary. But there's another reason, in addition to the data structure being explicitly designed for this use case, which is that it's much faster for lookup tasks. So the index operation, the dot index, is slow. That's a linear search through the array. It starts at the beginning and searches until it finds a match. And for a very big array, of course, this one's very small to just fit it on the screen, but in general, you'd typically be dealing with larger data structures, and the speed really makes a big difference. Incidentally, if you're used to doing things in spreadsheets, the VLOOKUP function is how you do this. And VLOOKUP does not use a dictionary. It actually has to do linear search for every match. So for a very big spreadsheet, VLOOKUP has significant performance problems. So this is just kind of an example of how data structures really matter. Okay, here's my follow-up question, or rather my second question. So I want you to abbreviate the following piece of code to a single line. So you have 4 lines of code here, and I'd like for you to practice putting some text before the code block. So you'll write a little text, and then you can hit Shift Enter to get a new line, and then 3 backticks and a space, and that will give you the code block to paste in some code here. And that way I can better match your solution based on the prose content. Cool. So I gave this exercise specifically because it's a sort of minimum working example of a list comprehension and the spelled out for loop version of it. So you start with an empty list, you build up that list one step at a time, and then return the result. That's the same thing as doing this list comprehension, where the for loop part goes in here, and then the expression generating each value goes in this first position between square brackets. So yeah, this is a list comprehension, and people were pretty on the ball with that and weren't so much when we first encountered this. So that's good. This is some feedback to me that there's some good retention here. By the way, when I ask questions, you're welcome to ask questions in reply. You don't have to just provide an answer. You can also, if you're confused about something, because I usually have time, especially early on as people are still coming up with their answers. If there's a quick question that you have right off the bat, I can fire back a quick response. So when I ask a question, it's not just sort of, one back and forth. We can have more. So, okay, here's my next question for you. So this is the last one before we pick up with the next thing. So suppose we want to sort a list of strings, but instead of doing it alphabetically, we want to do it so that shorter strings appear first and then longer strings appear later. So write some code to do that. And here's some code to kind of start you out. And by the way, you can work in this space now that I can track this just like I can track this one. So feel free to do your work here. You can go ahead and send what you have if you're not finished, and that's fine. I understand not everything you submit represents a complete solution because there's limited time, but feel free to just go ahead and hit send. Okay, so folks are coming through on this. So yeah, the key thing to know here, this is sort of a memory exercise more so than a problem solving exercise in some sense. The key thing to remember, pun not intended, is that key is a keyword argument that you can supply to the sorted function, which will tell that function how to sort. So it will give it a function that it can apply to each element of the list that it's trying to sort, and it will sort based on the returned value of that function. So we can say for any input string, compute the length of that string, and then use that result as what you're going to sort on. And the reason we would typically have an anonymous function here, you could name it, but usually you're going to see an anonymous function in this situation because it's something very small and kind of easy to write quickly. So just show you that this works. Yeah, and the strings are getting longer here as you move left to right. But incidentally, in this case, we don't need an anonymous function because the function that we're applying just is the len function. And in Python in general, it can be tricky to remember exactly what's a function and what's a method. So what is called by the traditional function syntax, like here we have sorted appearing in the first position rather than grandmasters.sorted. And it kind of matters for convenience for things like this because you can say key equals len and this works fine. I'll show you that this works. Whereas if it were the case that you have to call .len to get the length of a string, you would have to do a lambda here. It would look like this. Okay, but that would be if len were a method. Instead, it's a function. So it appears in the first position, and therefore we can just get rid of all of this and just say key equals len. Okay, so with those exercises out of the way, let's move on to continue what we were discussing last time. So if you recall, most of the lesson was dedicated to designing a spell correct function, which just takes a string and tries to return the corrected version of that if it is a misspelled string. Or sorry, if it is a misspelled word. So the main idea we had was to look at words which are one edit away from what was typed, in other words, from the input, and then see if any of those are words. And if so, then return the most common one. And if not, then check one step away. See if there's something that's 2 edits away instead of 1. That's a word. So here's the code we had. It's important for me to give you all of it so that you can run it and have it live in today's session. So we pulled in this big text from Peter Norvig's website. Then we separated the text into words using regular expressions. Then we looped through all of those words to build up a dictionary containing tallies for those words. So how often does each word appear? And also indirectly that contains the information about which words appear and don't appear. And then the first thing that we did was we wrote a function to generate one particular kind of edit, which is deletions. So if you have a string of length k, there are only k possible positions that you can remove a letter from. So for example, if we remove a letter from the, there are 3 possible ways we can do that. So we get 3 distinct strings here. And we checked that this particular way of defining this function works. But deletions are kind of the easiest to edit. We want to think about maybe a little more complicated one. And we'll jump into that now with insertions. So try to write a Python function which returns every possible string obtained by inserting a letter at some position in the input string. Okay, so it seems that this was quite a challenging one. It's definitely more challenging than the deletion. So let's work through it together and kind of see how this goes. So what we can do is we want to loop over the positions of the string. So we can say for k in range len of string. And then we also want to be able to insert at the end. So we'll do len of string plus 1. And then what we want to do, well, in some sense, what we want to do is say, cut the string at position k. So something like this, go from the beginning up to position k and then go from position k to the end. This would just give the original string back though. What we want to do is insert a character in here. Let's call it C. That's going to be our insertion character. And we have to do all the possible values of C. So we need to say for C in ASCII lowercase. So we're inserting all the letters here. And well, what are we doing with this stuff? We compute it, we need to keep up with it. So maybe we start with an empty array and then append. So as we go, we're tacking on this new value that we came up with. And then at the end, we can return that result. Okay, so let's see if that works. Oh, I forgot to do return. Okay, great. So that works. And by the way, you can abbreviate this as well. So list comprehensions are not just for situations where you have a single loop. What you can do is just copy this first part of the for loop here, then the second part of the for loop here, immediately after with just a space. It looks kind of funky. It kind of all runs together, but that's how it is. And then the generating expression, just like a regular for loop, comes at the beginning. And I'll put a carriage return here and indent so that it's a little clearer. But then that's it. So that kind of cuts out all this stuff. All right, and this is also going to work. So I'll send you what I have. So it's a list comprehension with a double for loop. And the thing to remember here is that the for loops appear in the same order as if you wrote it out the longer way. It kind of seems like from a math point of view, they should appear in reverse order, but that's not how it is. You put the for loops in exactly the same order. So if you write it out the long way, you can just copy them down in order and then put the generating expression here. And it helps keep your code more concise. Yeah, so we've just explained this, but I'll send the message anyway for completeness. This is the long version. So that way it's on the transcript. So it would definitely take a long time for us to walk through every single operation. So you get the idea, they're all fairly similar. I'm just going to show you a function that computes all of them at once. And the way this function is designed is first of all, we have all our letters. And so it's just really just making a shorter name for this. And then the first thing we can do is compute all our splits. So you're going to have to compute the splits separately for each kind of edit. And so might as well just do it once and reuse them. So we're going to have an array of tuples here. So we can loop over it and grab the first one and grab the second one and do stuff with each one. So capital L and capital R are going to be names for the two elements of this tuple in each split. And then the deletions, transposes, replaces, and inserts, it's all just a matter of changing up the generating expression a little bit and maybe changing up the for loop that we get here at the end of the generating expression. So the deletes are, the first part of the split plus the second part of the split with the first character removed. The transposes involve taking the left split and then switching around the first two letters in the right split and then taking the rest of it. The replaces involve the deletion. So notice this generating expression is the same as this one, except it's got an extra character thrown in. And we therefore also need to have an extra for loop in the list comprehension. So this is basically what we've already seen with the inserts, except just an extra slice here. So, this ends up being the same. The only difference here is that we have an if clause just in case the right split is empty. So that's included in the way that we define splits. And if the right split is empty, then we don't want to include that particular split. So we can put a filter here. Same idea here. If the right thing is too short for us to do the transpose at the end, we have to exclude those explicitly. And Python makes that really easy. You just put an if clause here at the end of the list comprehension right before that closing bracket. Okay, and then once we get all of those lists of different edits together, we concatenate all of them with the plus operator, and then we we apply the set function to that to eliminate duplicates and also store it in a set data structure where membership can be checked very fast. So a set is really just a dictionary behind the scenes, except there's not really values, there's just the keys. Okay, so that's what's going on with this function. I just wanted to walk you through that instead of doing each one as an exercise, just in the interest of time, because we do have other things we want to do with this that are going to be interesting and kind of take us in a little bit different direction. Okay, so let's try it. So if we call edits one of strawberry, we get all of this stuff, everything you can get from changing the spelling of strawberry in one of these sanctioned ways. And there are 544 of these, as it turns out. So you can ask for the size of this list. This set. You're going to get 544, which is kind of a lot in terms of scrolling up and down the page. But in memory, this is small potatoes. Python can handle this very fast. It's definitely totally fine for a real-time spell checker. Okay, so I want to do the second edit level. So we want to apply all of the allowed edits in the edits one function in order to get an edits two function that tells us all the strings that are 2 steps away instead of just 1 step away. Yeah, I guess I thought I set this up as an exercise and I didn't, but I'll give you a chance anyway, even though there's not a timer on this one. I'll give you a chance to try to write something, like just take a couple minutes and see if you can leverage the edits one function to come up with an edits two function. Glad I gave you a chance to do it so I could see what the really important salient point is here from a learning point of view, which is that we have the function edits one, which enables us to take any string and take 1 step away from that string in this metric space, 1 edit away of any kind, and tell us like what are all the things we could get to in 1 step. If we want to take 2 steps, it's much better to leverage our function that allows us to take 1 step and just repeat it. Take another step from all of the places you can get to from 1 step from the original input, rather than reproducing all the logic. Because the problem, if you go back up here Uh-oh. I need to make this thing collapse. If you go back up here and grab all of this and start applying the reasoning of like what needs to change if I'm talking about two edits, it's going to get very messy. And now you've duplicated code. If you realize, oh, I need to do this thing a little bit differently, go in and add something, more kinds of letters or whatever, it's going to be extra work because you have to change it here and in your edits too. So this is a really clear case where code reuse gives you a lot of leverage and there's really no downside. So the idea is what we want to do is we want to say, like, basically for each edit, so for each string that you can get sort of one edit away, we want to take another step. So like we loop over all the things that you can get one step away. And then for each one of those, we ask, what are the things that you can get one step away from that? And then we just use that. There's really nothing to compute here. The E2 that's one step away is the thing that we want. So essentially we want, start with an empty list and then append E2 to that and then return that list, which as you probably know reflexively by now, we can do just as well with a list comprehension where we just put the generated value first, then we put the for loops in order. So the for statements, the beginning of the for loops go in order, just separated by spaces, just like that. And the thing is, we don't really want to return a list here because it might have duplicates in it and we don't care about those. So what we want to do is take that list and turn it into a set. And this works. But in Python, you can take out these brackets and then instead of generating an array and then, instead of generating a list and then generating a set from that, this will directly generate the set from this iteration specification that's inside. So it's just a little more memory efficient, a little bit faster. Once again, have to put return there. And so this works. So this is much more concise, much easier, and much cleaner from a code organization point of view than trying to reproduce the edits one function, but add that extra complexity there. So this is what compositionality gives you. Okay, so let's check it out. Here, I'll send you a message so that it's not just what I typed on the screen. I like walking through these things, but I also want to give you the code so you don't have to type it. So, okay, so yeah, this is exactly what I had up there. This works fine. So here's another small exercise. There's 138,000 odd strings there. That's a lot. How many of them are actually words? So you'll need to write some code. Yeah, so let's walk through it. Let me pop up my code cell here. So, all right, so we have edits 2 of strawberry. That's what we're talking about. And it has a lot of entries in it. And so what we want to do is filter that list. So we can say word for word in edits 2. And well, that didn't do anything. It just made it an array. But then we can apply that if clause that we looked at a little bit earlier where we want to exclude certain entries that would otherwise appear in this list. What we do is we just apply a condition necessary to be included. And all we have to do is just check, is word in the word frequency dictionary that we defined earlier? And that works great. So we end up finding out that actually it's only strawberry. And the thing is, if you haven't seen this before, this looks weird. You feel like this has to be wrong in some way because the word gets repeated here twice, or I should say the identifier or variable name word appears twice here. And I don't know, there's just something that feels wrong about that. But if you ask Guido, the person who created Python, he will tell you this is the way he thinks people should do it. There's also a filter function that you can use, but it's uglier and it also doesn't return a list. It returns a generator, which can be slightly annoying to deal with in interactive contexts. So this is really, for the most part, what I would suggest using for a filter operation. So you just do a sort of vacuous list comprehension, but then you add a filter clause on, and it is fairly easy to read. I mean, even if you didn't know what this was, word for word in words, if word in this dictionary, it sort of suggests the meaning. Anyway, this works and it only gives the word strawberry. So, Shabam, do you want to tell us about the word cat? Yeah, this is really a great point. My name is in there somehow. I guess one of the books has a Sam character. Interesting. Yeah, I guess this makes sense for really short words like strawberry. I mean, I chose that word on purpose because I think it's sort of clear that there are no words in the English language that are that close to strawberry. I guess strawberries, but that's one more edit. So there's maybe a kind of small thinking question here. We didn't tell the function edits1 to return the original word. We only told it to return words that were actually one edit away. So how did we end up with strawberry itself? Okay, so everybody's on point with that. Everyone gets a star. So yeah, there are actually a couple ways for this particular word. So the thing that people were keying in on, which is true, is that you're always going to get a word back if you take two edits, because you can have a deletion and then an insertion, or two transposes in a row. Lots of ways to do it. However, strawberry itself is one edit away from strawberry as well, because you can swap the two R's and you get the same word back. Okay, so anyway, we're getting pretty close to having all of this kind of wrapped up together. So here's a function called candidates, which just kind of puts together all the stuff that we've come up with so far. So it checks if the word itself is known. If so, then it's going to return that. And we also have, checking one edit away, checking two edits away. But something weird is happening here. If you've never seen this before, it definitely looks weird, and that's totally understandable. I'm curious if people know what this is, or can figure it out. How are we leveraging the or operator here to do something useful on this line of code? So Yash, do you want to walk us through what you think's going on here? Yeah, great. Yeah, that's a great explanation. So, and then I forgot who this was. Hardy highlighted the kind of really important thing here, which is that or is a short circuiting operator. If I ask you A or B and you already know A is true, you don't have to compute B. You know the truth value of the whole proposition. And the language is designed in that way. So if you compute an array, it computes every entry in the array and then does whatever you are going to do with it. But logical operators are different. Or and both short circuit. Whenever they can figure out that the return value for the whole expression, they will stop executing. So if when we call the function known on a list containing a single word, which is just the input, if that returns a non-empty set, then the Python interpreter is going to know it doesn't matter what any of this other stuff is, it all is going to evaluate to true, so I can just return this first thing. It's a bit of a cheat though, because the value returned here is not a true or a false. It's not a Boolean. It's a set, and you have to have some understanding of what it means for a set to be what's called truthy or falsy. In other words, does it behave like a true or a false in a logical statement? And some languages don't let you do this. We'll see. Julia does not let you do this. You have to write your logic more explicitly in a way that every time you do a logical operation, you're doing it with an actual Boolean value. But JavaScript is very flexible like this. Python is pretty flexible with how it lets you deal with logical operators. And it allows for this is pretty nice, concise logic that avoids having to loop and stuff like that. It just goes through these lists one at a time, or rather these sets. It computes the set, and if it's non-empty, it returns it. If it's empty, then it proceeds to the next one. So this is exactly what we want to do here. Yeah, and as Shabam has already pointed out to us, some words have more distance to neighbors. Like even something like something has 4. So we've seen cat has a lot, something has 4, and strawberry has just the 1, or 0 really, if you want to explicitly exclude the word itself. So what we want to do is therefore choose, like, out of this list, what's the one that is most common, so we can return that one. And we can do that with the max function. So just like the sorted function, the max function returns, accepts a key argument. And so we can do something like max of candidates of strings. So give me everything that might make sense, and then find the most common. In other words, choose the maximum based on the value returned by this word frequency dictionary. And here we do have to use an anonymous function, or at least we can't just say word underscore frequency here, because word underscore frequency is not a function. It's not called like a function. It's called with these square brackets. That's a lookup operation or an indexing operation. So we do need to spell this out explicitly in this way. In any case, let's run this and see how it goes. So I should have put print here so we can see all of these. So some of these you can sort of guess, like CANDTE, probably that's going to be candle. This one, I don't know. I don't know what the most probable nearby thing is here. And I don't know, this may be guessable, maybe not. You've already seen it though. Okay, so FOD, yeah, this should have been guessable. FOZ becomes FOR, that's an extremely common word. Candle, that one kind of jumps off the screen. All right, you get the idea. So it's helpful, I think, to share some concrete numbers when we talk about speed, like how fast is something. It really depends on context, what counts as fast and what's slow. And sometimes it seems a little disorienting because someone says Python is slow, and then you interact with the Python at the prompt and everything seems extremely snappy. It's basically instant. And you're like, what's all that stuff about it being slow? Well, it depends on context. So it's helpful to think about this a little bit. Here, the spell correct operation is having to do a lot of stuff. Generating the candidates is a lot of work, or it can be in any case, if you have to go to distance 2 away, and then computing a maximum over a fairly long array, like with something like a few 100,000 entries in it, it can take some time. And ultimately, trying to spell correct, like something like, okay, here I misspelled strawberry for you, so it has to go 2 steps in. It has to go to radius of 2, and it takes about 100 milliseconds. So that's a tenth of a second. And you can think, like, if you were actually using the spell correct, you could notice that it would be pretty fast, really fast enough. But you can tell the difference between sort of instantaneous, like a few milliseconds, and something that's taking 100 milliseconds, where it's a considerable fraction of a second. So this is really fine. You would be comfortable shipping something at 100 milliseconds. But in a real application, you would probably want to make it faster, because you don't really have a lot of leeway here. If you double or triple the time that the spell correct is taking, you're looking at 200-300 milliseconds. That's too slow. That's going to be noticeable. It's going to feel laggy for the user, and they're not going to want to use the product. So you would need to do something faster. And in reality, what people do is they don't use Python. So for these like real-time types of demands, Python is not really the best fit. It's designed to be, kind of resource intensive. It's super convenient when you have the resources, but it's not great for situations where you don't. Most of the time, you're gonna want to take advantage of, as much as the efficiency gains will give you. And Python is just not ever going to be the language that really does that for like real-time applications. So just to give you a little bit of a sense, this is kind of fireside chat mode. But I want to show you what this looks like in Julia, partly because it's extremely similar, and so you can start to see, as we do Julia and Data 1010, it's not going to be a big leap. So you download things in a different way. That's in a package called HTTP, but it looks very similar. You read it in, that looks very similar. You use some regular expressions and find all the words. This, it's recognizable. You can compute a tally with the count map function from StatSpace. This all looks very similar. This is super striking to me how similar this is. We have our letters, we compute our splits, our if clauses are in here. This is all just almost the same. It's one index, there's an asterisk for times instead of an addition for string concatenation. But this is extremely similar. Look how similar this looks. It even has the double for loop comprehension. The filter can be done in the same way. This is the only thing that's really quite different. As I was mentioning, Julia does not have truthy and falsy values. It only has true and false. So what you have to do here is say, okay, for each of these functions, decide whether to return. So I'm kind of short circuiting here by returning from the function early. That's kind of the only way to achieve that functionality in Julia. But in any case, you can time this, and actually what you're going to find is that it's slower, which is disappointing because, it's Julia. The point is it's supposed to be fast. It takes like 300 milliseconds instead of 100 milliseconds. However, the reason this is going on is that, the first time you run it, the very first time a function runs in Julia, it has to compile stuff. So Python doesn't do this. It always just, eats your code and spits out the result. Julia does things differently. It kind of takes its time in the first iteration to prepare that function call to be much faster on subsequent iterations. And you're going to get a speed bump of about a factor of 2, so like 50 seconds versus 100 milliseconds. However, on real hardware, like on a local, your own laptop, the difference is much, much bigger. I don't really understand this. If you run it in the cloud on Binder, the difference is not that big. If you run it on your laptop, it's like 10 times faster. So it gets down to like 6 milliseconds. This is probably pretty close to what you would get from, C++ or some low-level language where you're really trying to squeeze the performance out. This is probably just about how long it takes, but that gives you some slack. That's pretty good. And you don't really care about that very first evaluation in a real application. You're going to be spell correcting a lot of words, so the payoff really makes sense. But in the real world, people don't use Julia for this either. They use a language like Swift, which is designed explicitly to build apps for the iPhone, or maybe Java for Android. But these languages are going to do the work ahead of time, and what's delivered to the phone to actually run, or what's going to run, in an app on a user's computer, is going to be compiled, and it's going to run about as fast as Julia, but without the startup costs, and it's going to be much lighter weight. So yeah, I mean, that was a bit of a diversion, but I just kind of wanted to highlight for you how Julia and Python are a little bit different from each other, and how they're both different from languages that actually, ship in production software where there's millions of users. They're going to be executing the code. But in data science settings, usually we're not so worried about that. We're kind of on the opposite end of the spectrum. We have a lot of resources and a lot of time, and the important thing is insight, and so that makes languages like Julia or Python a really good trade-off. And then, if you work for a company like Fitbit doing data science, and you have some great ideas that need to be implemented and shipped on actual, kind of low hardware devices like Fitbits, then there's going to be a team of software engineers writing Express software specifically for that purpose. So yeah, the stuff at the end there was, as I said, a bit of just kind of a chat. Obviously, it's not as important as all the practice and stuff. Part of it is just want to make class a little bit different from the reading. We're at 11 o'clock. I'll sort of officially adjourn class here, but there are a couple of questions, 3 questions that came in, and I want to. Well, I'll just take the time to answer these questions. If you want to hear the answer to these questions, hang around. You can also just look at the YouTube video later. I'll leave this stuff in. Okay, so about the actual application we were working on, Shabom has the following question. So order matters. So if if the original thing is a word, it returns that. If the first thing is if there's something that's 1 step away, it's going to return that. It's not even going to look 2 steps away. That's absolutely true. This does not handle the case where a 2-step misspelling is more common than the 1-step misspelling. Yeah, it's exactly right. There's no trade-off here. We're just going 1 step at a time. In some sense, there's an infinite penalty for being 2 steps away. We don't even look at that unless there's nothing available in the first couple of passes here. So that's right. We're not accounting for that. We need a different approach to do that. We just have to change up this last function, though. We wouldn't have to change up everything. So Hardy is asking about warm-up time for Julia. Yeah, this is definitely something people think about a lot in the Julia world. So is there a way to run the function behind the scenes in a way that makes things easier so that the user doesn't see that first penalty? So that's absolutely right. If you were going to ship something like this in a production app, which you wouldn't use Julia typically for that, because you wouldn't want the user to have to pay the runtime costs of a running Julia session. You want something that compiles and runs directly on the user's hardware. But yes, if you did want to do this, you'd probably schedule a first evaluation before it's actually needed. So you can do that in Julia for yourself using something called package compiler. And it's still it is a bit fiddly. There's some packages that will fuss, so it's not a perfect solution, but this will help you pay less startup costs. What it does is it saves a disk image with the compiled version embedded in it, so that you load that disk image back up and you're good to go. You don't have to wait for things to recompile. Another approach is to interpret Julia code the way Python does, and then only compile it and run it in that faster mode when you see that it's actually being called multiple times. This is the way JavaScript works, incidentally. So your browser runs JavaScript extremely fast, like way faster than it has any right to. And that's because it has an enormous amount of effort that Google put into making the V8 engine to exploit tricks exactly like this. It does some very, very sophisticated, smart stuff behind the scenes. Okay, and then Nick has a question about the numba package. So in Python, you can make things faster with a number of packages. So numba, pypy, or Cython. So I actually wrote a Quora answer kind of looking at these various options. And there are a few others, but I'd say these are the main ones. I'll just mention here what's going on with each of these, because it's actually pretty relevant knowledge if you are going to be using Python in a production setting. So actually, I have experience doing this. I worked for a hedge fund, and at some point, so the hedge fund's out of business now, so there's no IP concern about divulging hardware details and or rather software details. And basically, we had a situation where we had everything in pure Python. It was working fine, but we wanted to step up from daily returns to minutely returns. And if you've ever counted, there's a lot more minutes than days, and so the computational demand increased. The pure Python stuff just completely failed, and we had to make things faster. And so what I did was implement the sort of hot parts of the algorithm in Cython, and then we called into that, and it worked fine. So yeah, so basically these three things. So PyPy is, I would say, the least useful most of the time in data science, because it's a completely different implementation of Python. It doesn't, the reason it's called PyPy, it's actually implemented in Python itself. And the reason this is not so great right now is that a lot of things are designed to work with the main Python. And so if you have a completely different implementation, everything that's sort of designed to work with the main one has to be ported over somehow. So if you're running pure Python code, it's completely fine, and it is way faster than regular Python. But if you need to use packages that use other stuff, like certainly pandas is in that category, the SciPy stuff, NumPy as well, although NumPy does now work in PyPy. But you're just very quickly, if you start using this, you're going to run into some sort of tool that isn't designed to work for it, that you really need, and you have to pay. So, some situations this might be okay, but it's not really great. The thing that I would recommend most of the time is Numba. So Numba is basically Julia for Python. It allows you to write a function and decorate it. So the way it works is, if you have a function and, let's say the squaring function, you do numba.jit or something like that. I don't remember the exact syntax. So this might be it. So you import Numba. I don't think I have Numba on the Docker, so we have to install it. But you import Numba and you just decorate your function, and then what that's going to do is just in time compile the function. So that's what JIT stands for. It's going to render this function into machine code that runs very fast. So this is great for when it works. The problem with these kinds of solutions, and Cython is very similar in this respect, you have to compile the stuff in advance with Cython, so it's a little less flexible. But then you don't pay the warm-up cost the first time you call the function. So that's kind of the trade-off. But for both Numba and Cython, the problem is you're basically writing, it's like you're writing C code, but in Python syntax. So there's this translation that goes on from the Python that you wrote to something that the compiler can actually digest. And Python just wasn't designed for this. So your hands are kind of tied. If you're writing something pretty basic, then you're going to be fine. But as soon as things get a little more complex, so you want to go back and forth between Python objects that you carefully designed to model your problem and come back into the kind of tight numerical code where you need things to run fast, there's a boundary there, and it's expensive to cross it. So it can be good for kind of tightening up specific numeric specific things, but it doesn't sort of compile through the whole language and kind of make everything sort of one coherent, very performant whole. So you're going to get that kind of thing from C++. Julia also gives it to you without paying as much of a cost on the complexity of the language or how low level you have to write things out. And that's kind of what Julia does. It's super cool. And so you see this for example, in the differential equations.jl ecosystem. That's a package for solving differential equations. It's extremely sophisticated and very advanced, incorporates like a lot of recent research for solving kinds of problems where traditional algorithms fail. And it's so good that people just use it from Python. They fire up a Julia session, they fire up their Python session, they call into the Julia session from Python to take advantage of that solver, or some solver that they need in that package, because it's that good. It's better than things that are, in some ways at least, than things that are available in basically any other ecosystem. And the reason is the ability to compile code and also express yourself using the idioms of the language and not have those two things be in conflict. Whereas in Python, they very much are in conflict. Like, think about if you're dealing with a list of numbers. You have Python lists to think about. You have NumPy arrays that you can store that data in. Or if you need to do something with a loop, you might have to use Numba. And how does Numba play with NumPy? It's not perfect. It's not, there's a lot of hard work that has to go into making those two things interface nicely. And you're depending on someone doing all that work in the way that you need it. There are real seams in the ecosystem that make these kinds of things not really perfect solutions. But to directly answer your question, to see the speed comparison, ultimately they're all kind of pretty much the same, because they compile down to, it caches out for the same thing in machine code, more or less, that's running on your processor. And so they're all going to be very similar in speed, at least for simple use cases. And for more complex use cases, the performance profile is going to end up depending a lot on the details.